Hi, this is Matt Roscoe at the University of Montana with a short video lecture for our Section 12-8 Perimeter and Area Relationships. Sorry I can't be with you today, but hopefully you can use this to get some sense of this particular chapter. So Beckman thinks it's important that we explore a little bit about the misconceptions about perimeter and area relationships. This is kind of an interesting topic because it's something that has shown up in the literature that many students as well as teachers think that as perimeter goes up, so does area, and that's not always the case. So let's talk about that today. So the first thing I want to do is tell you a little bit about two common misconceptions when kids are given graph paper and asked to calculate perimeter, and then we'll talk a little bit then at the end about how area and perimeter are related. I'm going to rely on you to explore these questions using a couple prompts. So here we go. So suppose that Danette finds the perimeter of the figure below by shading the border squares and counting them. So she concludes that the perimeter of the shape is 24 units. Explain why Danette's method's not correct. So I guess what we're thinking here is that Danette is trying to find the perimeter of this shape. So that distance plus this distance plus this distance, plus this distance, here, here. So maybe what we should do is figure out the perimeter ourselves first. 1, 2, 3, 4, 5. This top is 5. 1, 2, 3, 4. 4 units along the side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units along the bottom. 3 over here, so I guess if that was 10, then this was going to be 5, because 5 and 5 make 10, and that's 1. So the true value of the perimeter is going to be, let's see, 9, 19, 28. But Danette concludes that there's only 24 here, and I guess the way that Danette is thinking about this is she's thinking, well, I'll just count the number of squares on the edge, on the perimeter of the shape. So what she's thinking is this. She's thinking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And so she's getting this 24 number here. Maybe I'll just erase this and put it in blue instead. And the big question is, well, what's going on here, right? Why is 24 not equal to 28? And hopefully, just by the way that I wrote it up, that you can kind of see what went wrong here, and it has to do with the fact that Danette didn't count enough, unit edge length at the corners. So I think the way to explain it is that if we sort of take a look at one corner, she counts this one corner here once, when in fact there are 2 units of perimeter in that corner, and of course that's going on here as well as over here, as well as here, as well as here. But when you first look at it, you think, well, geez, then she should have undercounted by 5 because there's 5 corners. And so here she undercounts by 5. But then if you look real closely, she also counts 2. The second square, I guess the one that's right here. This one, she undercounts. I guess she counts a unit of perimeter when it doesn't have any perimeter at all. So I guess we have 5 units where she's undercounting by 1, so these are all minus 1s, right? She's undercounting by 1 on all of these ones, where she's overcounting by 1 on these ones, so that would be a plus 1. So the net effect is that she's under by 4, because she undercounts by 5 and overcounts by 1. So I guess the whole point of this particular activity is that perimeter is interesting in the sense that students often want to count squares along the edge, and I guess it makes sense. They think of them as borders. They're trying to make sense of the object, and but it doesn't work because of the fact that, the corners basically lead to either under or over counts, depending on if they're inside corners or outside corners. So I hope that makes sense. This is a common misconception about perimeter. And you can kind of see that area is sort of, it's sort of in there, right? Because she's counting unit squares. This would be, in effect, what she's counted is the area of the perimeter border in squares instead of the actual perimeter itself. So something you will undoubtedly run into if you get to teach perimeter, and especially shapes that are drawn on square grid paper like this. So be prepared. Here's another typical misconception about perimeter. When asked to draw a shape with a perimeter 14 units, she drew the shape below. Is the perimeter truly 14 units? Why or why not? Well, we certainly can say that we've got 2 here, we've got 4 here, 3 here, and 3 here. So it looks like 2, 4, 3, and 3. Let's see, we get 6, 10, 12. So, I guess, let's see, 7, 8, 9, 10, 11, 12. Yeah, 12. And then I guess the idea here is that, well, since I went sort of up 1 and over 1, I could count this one as a 2. Is it really 2? That's the big question here. And indeed it's not. The reason is that if we think of that little corner cut off, it's the distance, right, between any two, the length of the diagonal of this little triangle I draw in a unit square. And of course these are 1s, and so we have something of the form right triangle with 2 legs that are known. So we'd have 1 squared plus 1 squared equals x squared. So 1 and 1 make 2, so 2 is equal to x squared. That means that x is equal to the square root of 2. If I hit that on a calculator, I'll get 1.414 ... It's an irrational number, it turns out to be. So not only is it not an integer, but it's actually a number that doesn't that can't be expressed as the ratio of 2 integers either. It's not a fraction. So she's wrong, right? This is not 14 units. So the correct answer would be this is not 2, it's the square root of 2. And so what would we have? We'd have 12 plus the square root of 2, so the perimeter is equal to 12 plus the square root of 2, which is just shy of 14. If I sort of plug that in, I get 12, 13.414 ... So it turns out that, this idea of like moving diagonally on the square grid leads to some pretty unexpected results for students that you're going to have to be prepared for. And I guess the way that I would always explain it would be, they're probably not going to know about the Pythagorean theorem at the point where they're trying to draw perimeters of a shape. So I just get out a ruler and measure it probably, right? It's reliably longer, right, than a unit. So I'd have them measure this distance here, I guess, find out how far that is, and then come up here and compare it, right, to the diagonal. And of course, you should get something that's like that in terms of length. So, and you can, if they really push it for it, you can say, well, it's a special number. It's called the square root of 2, which happens to be, closer to 1.5 than it is to 1. You'll learn more about that in 8th grade. All right, so those are 2 real common perimeter and area misconceptions. Let's get on to the real business of today, and that is how are area and perimeter related. So what I want you to do here is to do a short exploration. Would you, let's just take a look at a rectangle that has a perimeter of 24 units. If we suppose that a rectangle has a perimeter of 24 units, what can we say about its area? So we're going to use grid paper. I've placed a handout in the Canvas page, so if you don't have any grid paper to draw on, you can download that and copy it off. Draw at least 5 different rectangles that have a perimeter of 24 units. Include some rectangles have side lengths whose lengths are not whole number of units. And then would you find the area of each of your rectangles and write it on the interior of the rectangle? And then considering the rectangles ordered from least to greatest, what do you notice and what do you conclude? Okay, so but I ordered from least to greatest areas, I guess what I wanted to say. So let me just do a couple just to make sure everybody's on track here. We have the fact we're given that the perimeter of all of these rectangles is 24 units. I want you to draw at least 5. So I'll draw 1, for example. I could draw 1, 2, 3, 4 by 6, 1, 2, 3, 4, 5, 6. So here's your 4 by 6. So perimeter is equal to, oh wait, I want perimeter of 24 units. What am I doing here? That doesn't work because 6 plus 4 and 6 plus 4 makes 10, right? So let's see, one option. So let me think this through again. Rectangle 1, if the perimeter is equal to 24, I'm going to draw it. Let's see, splitting into half, that means half the perimeter is 12. That means the length and the width have to sum to 12. So I guess what I'll do is a 4 by 8. So let's try that one first. 1, 2, 3, 4. 8. 3, 4. 6, 7, 8. So here I have a rectangle that is 4 by 8. So the perimeter is equal to 24. And the area is 4 times 8, or 32. Another possible one would be, let's see. I could choose a perimeter of 24 again. So length plus width has to be equal to 12. So I could let the length be equal to 2.5, and the width would then have to be equal to 9.5, right? We could do something like that. Let's see if I can fit it on here. 1, 2, 3, 4, 5, 6. Yeah, I can fit it on. Let's see, 2.5, so about there. 2, 3, 4, 5, 6, 7, 8, 9.5 would be about right to there. 2.5 to here. 9.5 here. So 2.5, 9.5. So the perimeter, we say, then is still equal to 9, 10, 11, 12 times 2, or 24, just what we wanted. But the area is going to be different, right? It's 9.5 times 2.5. Let me hit that on my, can't do that one in my head, but here I get 23.75. So quite a bit of a difference in area. So that's what I want you to do. I want you to do that 5 times, and then to share your results in the discussion. Just take a picture of your 5 rectangles, and ultimately what I want you to really consider as you're doing this, once you have, consider the rectangles ordered from least to greatest in area. What do you notice and what do you conclude? In other words, right now, if I ordered them from least to greatest in area, I would say, well, the 2.5 by 9.5 is smaller in area than the 4 by 8. And hopefully you'll conclude something after you do this for 5 rectangles. And we'll talk about this when I get back. But go ahead and post your answer to that in our discussion for today. So that's one thing I want you to do. And then the other thing I want you to do now is to move this on this area and perimeter question onto an unrestricted figure. So in other words, so what about if I am not restricting myself to rectangles? And I guess the best way to sort of explain this is with, an applied problem. Suppose we have a forest that's on flat terrain and has a perimeter of 200 kilometers, but there's no information on the shape of the forest. What can you say about the forest's area? So to help you think about the question, I would tell you to imagine the perimeter, this 200 kilometers, as a loop of string, 200 kilometers in length. And the big question is what area can the loop capture? So think about that and maybe draw some pictures, but ask yourself, well, what would I do with a loop of string to make the largest possible area for the forest? And then if I knew that shape, is there any way to tell what the actual area would be? In other words, is there a ceiling? Is there some largest possible area, given that I have 200 kilometers of string in a loop? And then what about the range of areas? Do you think if we know the largest, can we get, what other areas do you think are possible for the forest? Is it possible to have an area that's smaller than that? So think about those two questions, maybe make some sketches or drawings, and then just respond with your intuition in the discussion for this chapter. All right, that's really it for today. If you post in the discussion by Friday at midnight, then you'll get credit for being in class on Friday, even though we're not meeting physically. All right, I wish you all a safe and happy break, and I'll look forward to seeing you all when we get back later on this month. Take care, everyone.